Hi, I'm Lucy, and this is the first part of the Circle Theorems Explaining series, where we look at the proof behind all your favourite theorems. Today we will be looking at the angle at the centre is twice the angle at the circumference. This circle has a centre, O. Let's add an angle. Two radii subtended, joined by the green chord. Another angle will be added to the chord. This angle meets at the circumference of the circle. To prove this theorem, we begin by drawing a line in blue from our angle at O to the angle at the circumference. This line spans from the centre of the circle to the circumference, so it is a radius. Next, we will label these two angles x and y. Let us zoom in for a second to angle x. You will notice, with the addition of our blue line, it is now contained in a triangle with two radii, two lines of the same length, an isosceles triangle. Now, what do we know about isosceles triangles? We know, of course, all their angles add to 180 degrees, but, more importantly, that the two angles on the baseline are equal. Therefore, we can label this angle also as x. The same can be done for the other side, for y. We go back to something that we said earlier to work out this angle here. Angles in a triangle sum to 180 degrees, so we will need to subtract the other two angles to calculate this one. So we do 180 minus x, or 180 minus 2x. Again, the same can be done on the other side. We get 180 minus 2y. Now, we add these two angles together to get the value of the reflex angle. 180 minus 2x plus 180 minus 2y, and when we group our integers together, we get 360 minus 2y minus 2x. Finally, we work out the angle at the centre. Another essential thing you will need to know is that angles around a point sum to 360 degrees. Here, the point is the centre of the circle. We need to work out the difference between our reflexive angle here and 360, the total, to get our angle at the centre. To do this, we must subtract the reflective angle from 360 degrees. So we do 360 minus brackets 360 minus 2y minus 2x. When you multiply the bracket by the negative, this becomes 360 minus 360 plus 2y plus 2x, which, when you subtract 360 from 360, gets you to 2y plus 2x, our final value for the angle at the centre. But how does this compare to the angle at the circumference? It should not be a challenge to work out what that angle is, as it is already labelled, x plus y. It should be easy to see now how our theorem falls into place. If you double the angle at the circumference, you will get 2x plus 2y, which is the angle at the centre. Similarly, if you halve the angle at the centre, you will get x plus y. And that is how you prove mathematically that the angle at the centre is double the angle at the circumference. Many other circle theorems are based on this theorem, but the most common application is proving that angles at the circumference subtended by the same chord are equal. Here we have a drawing of these two angles. It is subtended by the chord, shown in green. These two angles have something in common. If you add an angle at the centre, like so, and label it 2x, both of these angles will be equal to x by the laws of our first theorem. Therefore, angles subtended by the same chord are equal. Thanks for watching. Be sure to subscribe to see more GCSE and A-level maths, and don't forget to hit the like on your way out. Until next time, mathematicians.